Okay, now it's 5 past 7, so we'll start the session. Thank you for joining in, and I welcome you all to AI Fridays by AI Lounge. Today we have our very own Dr. Hassan Akil, who is also the CEO and the founder of AI Lounge. Welcome aboard, Dr. Hassan. Today he'll be talking about concurrency in Python, and I hope that this will be a very beneficial topic for everyone, and you will learn a good deal from this lecture. So over to you, Dr. Hassan. Please unmute and start your session.
All right, Assalamu alaikum everybody, and welcome and good evening and good afternoon.
Dr. Hassan, you are not audible, I think.
You cannot hear me right now? Okay. Is the voice better now? Okay, so it seems some people can hear me. So Adeen can hear me. Are there other people who can also hear me?
Yes,
okay, great.
Thank you.
All right. All right, so welcome everyone. So my name is Hassan, and I'm going to be talking about concurrency in Python. And so let me first quickly share my screen. Okay. All right, so I hope you guys can see my screen right now. And so the topic of this talk, of course, is boosting Python speeds with concurrency. And this is basically really concurrency and parallel programming more from a data science perspective. So my objective with this workshop or with this webinar is to kind of cover some of the topics that allow you to maybe boost speeds for Python workloads, and especially for data science type of workloads, because as a data scientist, you always want to increase speeds, of course. Python on its own really is not a programming language which is very famous for giving you excellent speeds. But in terms of data science, the type of capability and the type of performance that it gives you really, that's just really very powerful, and you just can't ignore it. So we're going to talk about this today. Of course, this is a really broad and a very vast topic, so I really won't be able to cover everything. And my plan is to maybe do like a series of webinars, maybe at least one or maybe two more after this, so we can kind of cover some of the main topics. And so today I'm going to be talking about overall an introduction, and then talk about IO-bound type of workloads and how you can actually boost your speeds in those type of scenarios. And then whatever is left, maybe we can do one or two more after this. Okay. So let me just. Turn the closed captioning on as well. And so the outline, of course, is to introduce concurrency and the types of concurrency, and then we'll primarily be talking about concurrency in Python. So what are the different libraries and packages that are available to you in Python as far as concurrency and parallel programming is concerned? And there are primarily three main tool sets that you have for concurrency in Python. The threading library, the asyncio library, and then the multiprocessing package. And I will already be introducing the multiprocessing package today, so I really don't have time to talk about that in too much detail today, but I'll just introduce it and then maybe we can cover it in more detail in the next talk or the next webinar. And then finally, is concurrency that something that you should use every time? So to be or not to be concurrent, because it's not really a magic pill. There are certain situations where you benefit from using concurrency, but then there are situations where you actually do not get any benefit from using concurrency. So to be or not to be concurrent, that's the sort of thing that we are going to try to figure out in this lecture. Right, now I will also be showing you some code in Python. Just a word about this, of course, these packages, especially asyncio, they're constantly evolving. And you don't want to use like a very old version of Python. I have personally tested all the code that I have that I'm presenting today on Python 3.7.6 on a Spider IDE, and it kind of seems to work really well on that. So I would recommend that, if you're going to be using the code, probably try something which is at least Python 3.7 or above, okay? So just to kind of ensure that all your examples basically run problem-free. All right, so what is concurrency basically? If you look at the dictionary meaning of concurrency, concurrency basically means to run things in parallel or at the same time. Now, that to some extent makes sense, but if you're like kind of looking at computer science, concurrency doesn't mean to kind of run things in parallel. It could also kind of mean that you're also maybe running things out of order, or you're maybe kind of time sharing a single channel. And as long as you kind of get the overall improvement in throughput or speed, then you're kind of basically using something called concurrency. So concurrency would not be just running things in parallel. It could also be you're kind of going more or less in a sequence, but maybe you're kind of running things out of order. So in a normal sequential program, when you actually write it, something that comes later may kind of get executed earlier than it is supposed to be in the sequence of that program, right? So I'll talk about this in more detail, and when I present you some examples, it actually will become more clear. But just wanted to highlight here that there are key differences between the dictionary definition of concurrency and what we actually mean with concurrency in computer science. And the way that I kind of see it, parallel programming or parallel computing basically is more or less a subdomain within concurrency. So concurrency is more broader as such. All right, and some examples where you actually might see concurrency, or some scenarios might be, multiple computers connected to a network. It might be applications, multiple applications running on a computer. Your operating system on its own is obviously doing a lot of concurrency. So it's running or juggling very quickly between a lot of tasks. And to the user, it kind of seems that things are kind of going on or running in a sequence, but actually they're running concurrently or in parallel or out of order. But as long as the end user experience remains the same, it doesn't really matter. Okay, and then of course one more example is multiple processors on a CPU, where you again kind of run some programs on one core and then other programs on another core. And these days, most systems that are out there basically have multiple cores, and so concurrency and parallel programming, of course, is widely used now. Right. So when we're talking about concurrency itself, concurrency typically results in increased throughput. Now, what we mean by increased throughput is that overall things tend to get done much more quickly. But this is typically, it's not always. So you won't always get a boost in speed, but if you apply it to the right scenario and in the right application, then typically you expect that you get significant or a substantial enhancement in throughput. But at the same time, it also adds complexity to your code, right? So because you're now managing more things, you're kind of thinking of things out of order, that kind of becomes more complex when you introduce concurrency. So one example that I would want to give maybe here is, maybe running like a single person enterprise versus scaling your company or your enterprise to contain large number of employees. Now, whenever you kind of scale your company to include a large number of people versus doing everything yourself, that tends to introduce increased throughput. You are able to do more things much more quickly, but it also has its own set of complexities, right? People are harder to manage, things get more complex, and so it does tend to introduce complexity. So if you don't do it right, then this added complexity may not actually give you much of an advantage, right? So just keep that in mind. So there are some trade-offs, of course, right? Now, as far as Python is concerned, why should we use concurrency in Python, right? I mean, if you look at Python on its own, and I'll show you some examples, Python itself is not a language which originally, when it was written, was designed for speeds. It was more from a perspective of making things easier to do. It was designed to be more high level than maybe other languages like C and Java. But why would we want to introduce concurrency in Python? Because a lot of the times, when you're doing parallel programming in concurrency, you have to kind of make this choice of, do we really want to do concurrency in Python? Why don't we just go down and do it in something like maybe C and Java? Now, the way that I see it as a data scientist, as a machine learning guy, concurrency is useful, especially in Python, for data scientists, because Python provides you a huge set of tools for data science, and if you are able to use concurrency to actually speed things up, it could actually still be beneficial. Now think about maybe reducing your training time from 4 hours to 2 hours, or maybe let's say 24 hours to 3 hours. If you use a little bit of concurrency, and if you're a little bit smart about it, then why not have that, right? So now with Python, yes, you still may never get as much of a performance boost as you may get in some other language, like maybe Java or something. But of course, with Python, you are dealing with a language which provides you a huge tool set of tools, or a huge library of tools for data science, and that of course also has a lot of advantages. So I would still say yes, use it. You may not get as great speed boosts as other languages, but it's still worth it, I think. So that's what I'm looking at. So I'm personally myself looking into concurrency more from a data science and machine learning perspective, and that's something that I eventually turn to or I intend to talk about in more detail later on. Right, so if we're talking about concurrency, there are basically two types of problems that you generally have to deal with when you're talking about concurrency and parallel programming. One of them, of course, is IO bound or input-output bound workloads. When we're talking about input-output bound workloads, those are the sort of scenarios where your speeds are bounded by communication delays. Right, so examples could be disk operations, where you have to do a lot of read-write operations from your hard disk. Another example could be network delays. So if you have to maybe query some database that is connected to some network, it would take some time to respond. The network speeds might actually slow things down. Now, do you just want to kind of keep waiting and just go in a synchronous or a sequential manner? Or do you want to maybe squeeze some other task and maybe utilize this free time that you have a little bit more efficiently, right? So rather than just sitting idle and waiting for your database to respond or waiting for your cloud to respond, if you're kind of reading data in, why not do something else in this time? So I'll show you a few examples, and hopefully this will make a bit more sense as well. So what we do with IO bound concurrency is that we kind of exploit these wait times between tasks to enhance our overall throughput. Okay. And then, of course, the other type of concurrency is compute bound, where we're talking about large numerical computations, so maybe working with images and videos, which is huge numbers that we have to process. Now, how could we actually divide this into smaller tasks and maybe run them in parallel on our multiple processor cores that we may have, or on GPUs? So those are the sort of loads which would be more compute bound. And again, in this, the approach is to divide your task into smaller independent subtasks that you can basically execute in parallel. Right. So within Python for concurrency, you have 3 libraries. The first one is threading, and then second one is async IO. Now, these two are primarily for IO bound type of situation. So if you have a program where you are doing a lot of read write or network operations, then using async IO or threading actually might give you improvements in performance. And then, of course, multiprocessing is more for compute bound loads, where you're trying to kind of take advantage of the multiple CPUs or cores that you may have on your system's processor. Right. Now, one of the problems with Python is something which is called the global interpreter lock. Now, one of the issues that you tend to encounter when you're working with Python and you're trying to introduce concurrency is that Python originally, and a lot of flavors of Python, when they were written, were meant more or less for single processor type of interactions. And so Python has something which is called a global interpreter lock, or the GIL. Now, what the GIL does is that basically it allows only one thread access to the interpreter at one time. So, only one of your threads or one processes within your program is allowed to communicate with the operating system at one time. And that kind of becomes a bit of a bottleneck. And what essentially it does is the variants of Python that do contain the GIL, it kind of limits them to single processor workloads. You can't really take advantage of the multiple cores on your system. There's a workaround, of course, to that. There are many workarounds to that, and we'll talk about that later on. So, graphically, if you're looking at it, and even if you divided your code into multiple subcomponents or threads, and you may want to execute them in parallel, what the GIL does is that it basically limits you to go one thread at a time. So you have thread 1 going ahead first, and thread 2 going getting access to the interpreter after that, and then thread 3 maybe getting the getting access after that. So it kind of is a bit of a bottleneck that you do have to overcome, but you can still work with this even with the GIL, because you could kind of switch between threads very quickly, and you could kind of time share the single thread that you have, but it is a bit of a bottleneck, and this is why some variants of Python have kind of completely let go of the GIL, and they don't have this. So if you're looking at the different variants of Python, CPython is the one that does have a GIL, and it was basically this GIL was enforced in CPython primarily because it ensured thread safety to when working with programs that were written originally in C. So it added or provided you a lot of features, but of course it kind of came at a cost as well. And if you're looking at Jython and IronPython, they do not have the GIL, and so over there you don't have really this issue of um, getting stuck with us with the guild. So now, what I want to do next is to show you some examples of latency and delays and where they happen inside a computer. And how we can kind of take advantage of these delays. So if we're looking at maybe IO bound situations, or if we have threads that are tasks or sub programs that are going to be waiting for a long time, can we actually time share the resources that we have? Now, if you're looking at our system, if you're looking at any computer, you have, of course, the CPU, which is the fastest part of your component of your hardware. And then the CPU can talk to the RAM, which of course itself is pretty fast. The CPU also can retrieve information from the hard disk, which as compared to the RAM is slower. And of course it can also, these days, because we're really heavy on cloud computing and talking to or retrieving data from the web or the cloud, we also may need to talk to some remote server that is connected to a cloud through our network card or some of our other peripherals. Now, this is something which is probably the slowest part, and it introduces the largest amount of delays, right? Because when you send out information and you want to get something from maybe, let's say, another continent, that will introduce a little bit of delay. In fact, if you're talking about CPU timescales, it introduces huge delays, okay? So, I mean, if I was to give you an analogy, the communication between a CPU and a RAM might be something like a Formula One sports car. The communication between the hardware and the CPU might actually be considered something like your dad's old van or something. And then if you're talking about communication through the cloud or through on the internet to, let's say, some remote database, or maybe communicating with some social media network or something, that you could think of as maybe a bicycle or something even slower. So, so you have this huge kind of disparity in terms of the tasks that you have to juggle and you have to do. And you kind of see that, if you have a task which requires maybe reading some information from this database, which is on the cloud, it's going to really slow things down. So if you have some request for some database query and you send it out, it'll be really, really slow. Now, you could just sit around doing nothing in the meantime, or you could basically execute something else in the meantime. So, maybe if there are parts of your program or there are sub parts inside your program which require disk reads or which require RAM access, you could actually schedule those in between, because this part is going to be really slow, right? So you could actually do, if you have things to do, you could just put them in there and then just go ahead and execute them. So let me give you one more example. So let's maybe look at a conventional IO bound workload. So let's say if I've kind of introduced this grid here, so you have programs which can either be or maybe waiting for execution. They could be active. And then if a program is active, it may ask you to do some task, and you may, your system may, in response, carry out some action. And then once a program is complete, then you probably put it down here in the complete box, right? So we're kind of talking about time as we're going in this direction, from left to right on my screen, right? And so let's say, we're looking at a conventional program, and we have three programs that are waiting to execute, and we're going to just proceed in a sequence. So once program 1 completes, then program 2 kind of becomes active, and then we wait for that to complete, and then program 3 basically gets executed. So everything is synchronous or in a sequence. So let's see what happens. So first program 1 becomes active, and then let's say it requires us to do something like maybe a database query. So the task is to query the database. You dispatch the query to the database. And then what do you do after that? Well, if you're doing things synchronously, you have to wait for P1 to finish, right? So you wait, and then you wait again, and P2 and P3 in the meantime are still going to be on hold. And then you receive the database query. So once you get the database query, let's say that's the only thing you want to do in program one. Say, okay, program one's complete. Right, so you just say that's complete. Okay, now once program one is complete, then you move to the next one and say, all right, now let's make program two active. So program two was inactive. I kind of said, okay, now let's look at this guy and let's see what he does. And let's say this is a web request. And what do you do after that? Well, you just wait and you wait and you know, and you wait, right? So this is clearly very inefficient, right? Now, what we want to do here is maybe do something like time slicing. So if we can, while we're waiting for some request to be entertained, maybe we can put the program back on hold and maybe bring in another program which comes after, activate that, see what it wants us to do, submit that request. And then, you know, if that requires waiting, we can wait for a little bit more time, and then maybe bring the next program in. So let's say we have P1, and P1 basically might be a database query again. So we dispatch the database query. And once we dispatch the database query, what we do is, I will say, well, thank you for coming, get back in line. We'll let you know when we hear back from the database. Okay, so P1, instead of staying active, kind of gets put back in to the queue. All right. And so what we do then is we say, all right, let's look at the next one. So all right, I'm sorry, I got muted. I got to unmute again. Okay, so now what we can do is, so program two basically is RAM access. You need to do RAM access. You maybe want to fetch some data from the RAM. Now this is something which is really quick. Maybe you can do it in one time cycle. And so program two, let's say, gets completed, right? So once it gets completed, you put that, okay, I'm done with this program. Let's just get rid of it. And then I can maybe look at program three. Now program three is a web request. We expect that you would have to wait longer for it. So you send out the web request, and then you put program three back on hold. And you say, okay, let me just see what happens. And then let's say in the meantime, what happens is your database query, which was originally sent out by P1 over here, that kind of comes back. So what you do is you wake up P1, you say, all right, P1 is complete. Put it in the list of complete things. And then what you do finally is once your web request comes in, then you can basically go ahead and you can kind of complete that program as well. So you're kind of, you know, in this case, you're time sharing things, you're time sharing your resources, but if you do it smartly, there's still a lot of efficiency that you can introduce in your overall system. You can really enhance your throughput as such. So now let's just compare the concurrent program, which basically just used time slicing. And so it did not wait around for a program to complete before it kind of asked the next, you know, before it let the next one go ahead and do something. You can see that, you know, in the conventional synchronous program, you actually have to wait around for a really long time, right? So that seems to be pretty inefficient. You're waiting here, and by this time, only one of the programs is complete. Whereas over here, you can kind of see that, you know, by the time you get over here, you have two programs or two threads in your program that are already finished, and you're just waiting for the last one. So that's how you kind of introduce more efficiency. So even within Python, you may have a single thread that you're required to access, or you may have the guild, but if you share it within these different threads or within these different sub programs, you can still introduce efficiency. You can still introduce or enhance your throughput, right? So you're kind of enhancing your latency here. Now, if we're talking about improving efficiency or improving throughput, there are other ways of doing it too, right? So let's say If your system has multiple processors, which most systems these days do have, so you have like 3 CPUs, or you could put one program on one CPU, the other one on the second CPU, and then the third one on maybe the third CPU. And of course, you're kind of doing 3 things simultaneously, so you would expect that your overall throughput maybe increases 3 times. I mean, you do 3 tasks in the same amount of time that you would normally or ordinarily do one task in, right? Now, that's good, but one of the problems with Python, and I mentioned this earlier, is the GIL, right? So the GIL is actually preventing you from increasing the number of threads. It only has one interpreter, so your threads have to go out in a sequence. So they have to go out one by one. How do you actually work around that? You can either use a flavor of Python which doesn't have GIL, or the other thing that you could do with multiprocessing or with this type of scenario is use the multiprocessing package, right? So the multiprocessing package basically was written to kind of circumvent this problem. So it allows you to bypass the GIL. So if you use the multiprocessing package, and we won't be talking about that today, but with the multiprocessing package, what you can do is you can actually split your program into multiple threads, and you can run those threads on separate cores of your processor. So it can be useful. So let's say you were doing some sort of image processing. Maybe you had 3 different filters that you needed to apply in parallel, let's just say. Or let's say you had a huge image and you wanted to kind of maybe apply some sort of convolutional filtering on it. Now, rather than just going and doing that filtering in a sequence, so one patch at a time or one sub image at a time, what you could do is maybe divide that into 3 kind of, or divide your image into 3 or 4 maybe sub images, and then take those small parts of your image and maybe execute each one of them on each CPU that you have. So that's multiprocessing, but we'll probably talk about multiprocessing next time if we do a webinar and I do a good enough job and you guys are interested in joining us next time as well. So hopefully you guys will. All right, now, when we do concurrency, what are some of the challenges that we end up facing, right? Because we're introducing complexity into our system. What are some of the challenges that we expect to encounter, right? So first one, of course, is coordination. So you have to kind of consolidate things after breaking your program into processes that may be executed out of order, right? So if things are executed out of order, you have to then at the end kind of combine things and sync them up with each other. Another thing is, if you're kind of breaking your program into different threads, you have to ensure that they don't end up conflicting with each other, right? So let's say you have 2 threads that maybe want to access a database inside some bank. Now, if they were doing things in a sequence, so once goes ahead, so the first program or the first thread goes ahead and adds a certain amount of money to the bank account. And then the second thread goes ahead and adds another amount of money to the bank account. Now, if this was done in a sequence, you would have no problems. But if you were doing concurrency, so if both threads kind of came along and tried to update the bank account at the same time, that would cause problems, right? So you have to have this coordination between threads to make sure that these kind of problems don't happen. You have to manage memory. So if you're dividing your program into multiple threads or multiple sub-programs, how much memory does each process get? Scheduling, so which process is active at what time? Again, this is something you'll have to manage. Deadlocks. Deadlocks is another thing that could happen, right? So you may have two processes that are just waiting for each other. And this is something which is very common when you're dealing with multiple threads. So you have two threads that try to access the same resource, and then both end up trying or waiting on each other to complete. So this is kind of that type of a situation where you have two aristocrats, or maybe two guys saying, all right, and you have one resource and they're saying, all right, I insist. And then the other says, no, sir, I insist. So if you're looking at maybe the Urdu analogy, you know, Nawab Saab maybe, sir, pehle aap and pehle aap, and that eventually both of them kind of miss the bus. So you could have the same sort of scenario occurring over here. Okay, so this is basically what a deadlock would be, and it's very common in threads. You could run into something like resource starvation. So you have shortage of memory and disk space and things like that. You could also have race conditions where two processes modify the same resource simultaneously. So again, this probably will happen because of lack of coordination between threads. So you are getting potentially getting enhancement in throughput, but you're also getting added complexity, and you have to be willing to be able to deal with that. Okay. So your code will get more complex, but that's a price that you have to pay. So enough slides. Now what we're going to do is, well, I have maybe a few more slides, but what I'm going to do is introduce you guys to some of the code in Python. Now, as long as you kind of understand the crux of what the code is doing, you don't really have to worry about what every line is doing. Okay, so we're first going to introduce the threading library in Python. We're going to kind of look at a sample program and maybe run it and see how threading basically works. So let's get down to it. Now, let me just quickly recall or again tell you, threading mainly is meant for IO bound workload. So let's say you're sending out a lot of web requests. That's a situation where you could use the threading library to enhance your throughput. Maybe you're doing a lot of disk operations. You're reading a lot of data from the hard disk. Again, if you use the threading library, you actually might be able to enhance your throughput. Okay. And then again, what this threading does is it uses time slicing. So when you're waiting for something, it will probably go ahead and schedule another task and sneak that in between during the free time and take advantage of the free time that your system has, right? So you're basically time sharing your resources between different threads within your program. So it could be like, maybe you sent out a web request, but in the meantime, if you had to do like a RAM operation, you could do that. Maybe you had to read some data from the hard disk, even though that may come later in your program, you could do that in the meantime and not wait for this thing to complete. Okay. And of course, this delivers significant throughput gains for workload that contains substantial disk or network operations. And another thing about this is that it stays within the GIL. So it kind of gives you the impression that things are kind of running in parallel, but everything is basically going on in a sequence. But what you're doing is, even though you're only sending one thread at a time, you're kind of switching between threads very quickly. So overall, you do get an increase in speed. So now let's start with a simple example. Now, before I actually introduce you to threading, what I'm going to do is I'm going to use a very simple synchronous program where I'm going to send out multiple web requests. And I'm just going to download data from 100 web links, one website at a time. So this is synchronous. This is a classic IO bound example. So you have 100 websites and you need to download data from them. if you do it in a sequence, it obviously will cause delays. So let's first try to do it in a sequence or in a synchronous manner. So maybe write a for loop and download from these websites one at a time. So I have this file which I'm calling weblinks.txt. And then within weblinks.txt, I have these 100 links that I've added. And I'm just going to each line one at a time, and I'm kind of downloading data from there. Okay. So let's quickly look at the sequential or the synchronous example. So let me quickly walk you through the code. So I have this file which is read.txt. So this is just reading my text file, which is just the web links. And what I do with that is, so actually this should, so I basically just give it this name of the file, weblinks.txt, which contains my files. And then what I have is I basically download all sites, but I download them one at a time. So within this, so this is my main function. I first read the text file. I put the text or the URLs, the 100 URLs that I have inside a list. Then I start my timer, and then I download my websites one at a time, right? So let me just go ahead and run this. And while this is running, I can maybe explain what this is doing. So you can see that the first request went through and then the second one. So it's kind of reading this. So download all sites. It basically requests a session, then uses that session to download a single data from a single URL or a single website. So what does the single URL do, or the download single, where it just downloads data from one website? So I basically go ahead and I kind of read data from this website that I'm passing in this list. And then, you know, this program should execute. So you can see it's not really fast, but it's still downloading data. Hopefully it should complete soon. So I have 100 URLs, reading data one at a time. And you can see, in fact, this time it was really slow. It took about 48 seconds, right? So this is fairly slow. So yeah, so if I go in a sequence, I'm basically going to take about 49 seconds, okay? Now what I want to do is I have 100 web requests. I don't really have to send them out in a sequence, right? Why don't I just send something like 5 web requests at a time? I mean, I could do that, right? So I could send like 5 and then maybe the next 5 and then maybe the next 5. So that's what I want to do here. So on the next program, what I really want to do is when I'm sending out my web request, rather than kind of sending one request at a time. So I'm still, of course, this contains only web requests. So instead of sending one web request, I kind of send out 5 web requests at one time. How can I do that? I have to use the threading library for this. So let me just now take you to the threading code. And well, first thing you're going to have to do is you're going to have to import the threading library. Then you're basically importing time. So this is just to measure the amount of time that it takes you to execute the whole program. And then there are some other libraries that, so requests basically is to get the session. So every session is going to be used to download one or data from one web link, okay? And then you also have to import concurrent.futures, which I'll talk about. So let's go to our program. Now it follows a similar pattern, but there are some key differences that we have to ensure because we are now doing things concurrently. Okay, so our code obviously is going to get more complex, but it's also going to increase the throughput as well. So we want to really reduce the amount of time that it takes to actually read this data. Okay, so let's look at this. So if I look at my main program or main function, what I'm doing here is I'm reading data from those text files and putting them inside a list. So I have a list which contains 100 URLs. I then start my counter, and then I basically have this function which is download all. Now this download all, basically I pass it the list containing 100 websites and URLs, and let's go back and look at this. So download all. So what does this do? What it does is it says, okay, use this function concurrent.futures .thread pool executor, and then it's saying max workers is 5. So what that means is it's saying, all right, I'm going to download these 100 websites, and I'm going to be using 5 workers or 5 threads to actually download these websites. So rather than sending 1 request at one time, I'm going to send 5 at one time, okay? And that should hopefully increase the amount of time or reduce the amount of time that it takes for us to actually execute this, okay? So once I do that, so I kind of create these executors, then basically I kind of use this function which is called executor.map. And then within this, I call the download single function. Now, what is the download single function? The download single function basically downloads these, one of these websites. So you obviously have 5, you have 100 URLs that you need to download from. You download using 5 threads. So you basically send out 5 requests at one time. And then this download single basically will download 1 website or from 1 URL at one time. Okay. Am I getting some questions? Okay, maybe I'll talk about the questions in the end. So let me just finish this and then we'll address the questions as well. Okay. Right, so we have a download single. So that basically fetches 1 URL at one time. Now, one of the things that you need to do here, which you didn't have to do previously, was you have to get 1 session for each of these 5 requests that you're sending out. You have to be really careful when you're using threading, because you're looking at this requests library, which basically gets these sessions. This thing is not thread safe, right? So this was written for the Python, which was basically, you know, operating in this fashion. So this this requests library expects that everything is going to come one at a time. So it's going to give 1 session to a thread. And then if another request for a session comes from the same program, what can happen is that this requests library can allocate the same session to another thread. So the first request basically gets discarded, right? And this is something that you need to ensure, right? So what you need to do is you need to make sure that you get 1 session for each of the 5 threads that you're sending out at one time. Because if you don't do that, then you will end up losing some of those threads, okay? So this is the part where, you know, you see that complexity coming in, right? You have to ensure this coordination, because, you know, a lot of the different libraries that are available in Python are not thread safe, right? They're basically written on the assumption that you're kind of getting 1 thread at one time, and you're not getting threads in quick succession, right? So they're not really written for concurrency. So this is something that you must ensure. So that's why we have this function here, which is get session. Now, you don't have to worry about everything line by line. I'll make sure that you guys receive the code as well, so you can play around with it later. So once you get a dedicated session for each one of these, you can download data 5 requests at a time. So let's go ahead and run this and see if we get any increase or boost in speed. Now, remember, when you were going in a sequence, things happened, you know, it took you around 48 seconds to download data from those 100 websites. Now let's run the concurrent version using threading. You can see things are much more quicker. And wow, so we kind of did this in about 7 seconds. Okay, so this is much more quicker. Let's do it one more time. All right, so pretty much the same time, 6 or 7 seconds. Now there's going to be a lot of variation in this time. When I ran this earlier, the threaded program actually completed in about 4 seconds when I did this maybe a couple of hours ago. And the synchronous one, which was basically going in a sequence, that completed in about 30 seconds. Now, this time obviously varies depending on what time of day you're executing these tasks, what is the load on the remote kind of server that you're talking to. So there's a lot of variation on this. Now, one thing that you need to figure out with multi-threading is you don't necessarily have to use 5. I mean, 5 is not a magic number. You could have used more requests than 5. You could have used less than 5. But you have to figure out what number really works best for you. Okay. So let's go back to the slides for a second and we'll come back to the code. Right. So what we did here was we basically had these 5 workers. So we kind of had these 5 workers that were being sent out at a time, even though each one of them is slow, but kind of sending 5 guys out at the same time. So, they bring in 5 times more information than sending out 1 guy at a time. Okay. And so what happened was your download all was kind of the part which was managing these 5 workers. So download all was saying, okay, I have 100 requests that I need to entertain, and I'm going to entertain these using 5 dedicated sessions, downloading each one of them in a dedicated session. So this guy was the one that was kind of managing or doing the coordination for you. And believe me, I mean, this concurrent.futures.threadpool executor is actually taking care of a lot of things for you, right? You can actually go further down. You can kind of run each thread on your own, but that thing makes things a bit more complex. And maybe a few years ago, maybe 5-6 years ago, that is something that you would have had to do yourself, but it has been simplified. So this threadpool executor actually takes care of a lot of things for you, all right? And then this get session, basically what it was doing was it was ensuring that one thread gets mapped to each session. So each of the 5 candidate threads that you're going to send out at one time, they don't end up getting the same session, because sessions is, or requests.sessions is not thread safe. So you have to kind of make sure that you actually get one dedicated session for each of these 5 workers that you have. Okay, so these are points that I've kind of talked about now. One thing that you kind of need to remember is that every time you add a new thread, it kind of incurs extra overhead. So the operating system actually has to do some extra work, okay? And that also introduces a delay, right? And so just because you were sending out 5 requests at one time doesn't necessarily mean that you're going to get a 5 times increase in speed as well, right? And that primarily is because each thread kind of incurs extra overhead. Now, I kind of briefly saw a question, how many requests can we, or how many worker threads can we have? We can have as many as we want, as many as our memory allows. But remember, if you create a new thread, it incurs extra overhead. The operating system kind of has to juggle between them, and your performance is eventually going to saturate, right? So don't just go like, if you have like 100 web requests, don't just go ahead and introduce or use 100 workers and then expect that you get a boost in performance. It might end up slowing things down. In fact, you could actually play around with this code and increase this and see what happens, okay? All right, so the next thing that I'm going to talk about, and I may end up going 5 minutes over time, but I think we started 5 minutes late, so I think I'm good on time, okay? So the next one we're going to talk about is the async IO library in Python, right? So this does something similar to multi-threading. So again, this is for the IO bound loads and IO bound scenarios. So we'll now write an async IO library or a program that uses the async IO library to actually do the same thing, and then see how that works, right? So now async IO as compared to threading is relatively new. It was introduced with Python 3.4. And it works, the way that it works is slightly more different than the threading library. Now they're both meant for the same tasks and the same type of workloads, but async IO actually, it has some key differences that we're going to discuss in a bit. But one of those differences is that with async IO, you have what is called an event loop, which kind of takes care of managing these different tasks for you. So this is kind of similar to what the thread pool executor was doing, but now you have somebody which is called the event loop, and this event loop is basically going to kind of manage the different threads or the different tasks that you need to run. And then the other concept that is there is basically okay, I think I lost my camera for a second. All right, you guys don't need to see me, I guess. I probably ran out of battery on my camera, I think, so let's not worry about that for a second. All right, so you have the event loop, and then the event loop basically takes care, so it manages these different tasks, and then finally you have the coroutines, which again is something that it's kind of like a part of your program which is going to take control of your operating system for a bit and then return that control after a while. All right. Okay. Sorry, I got distracted with my camera. Let me not worry about that. So now one of the things with that makes async IO different from multi-threading is that async IO basically uses what is called cooperative concurrency. Now, once you actually give control of your program to a coroutine or a subtask or a thread, it will return that control back when it wants to, right? So once you actually give control to somebody, you have to wait for them to kind of surrender that control. They won't do it on, so if they kind of take control and never return it, you really can't do anything about it. But so this is more cooperative concurrency. You're kind of dependent on these coroutines. So once you hand them control, you're kind of waiting for those guys to return the control. And if they don't return control, your program will basically get stuck, right? And then async IO basically uses two keywords. One is async, the other is await. And these are also kind of important, and I'll talk about these in a second as well. Now, one more difference with async IO and multi-threading is that threads are basically managed within Python, right? So if you look at the threading part, what actually happened there was you actually had these threads that were basically getting access or going into the operating system, and you had to kind of make sure or kind of juggle them or go to the operating system level and kind of manage them there. With async IO, all your threads are managed within Python. So the operating system still sees that single GIL type of a program that it has. So it doesn't know whether you're actually running things concurrently or not. So all of that is being managed within Python. So even if one of your threads or coroutines get stuck, The only thing that is affected or impacted by that is Python. So it doesn't really affect the other programs that are running on your computer. Okay, so and the other thing about this, of course, is that this also kind of makes async IO independent of the operating system. Okay, because everything is being managed within Python. All right, so let's talk about the async keyword and the await keyword before I actually show you the code. Now, what does the async keyword do? The async keyword basically indicates a part of the program that can run asynchronously. So let's say you have a function which basically is going to go ahead and download data from some URL. You can basically ask the program to actually wait, right? Okay, I'm back on. So I switched to my other camera. Sorry, I might not look as good on this camera, or maybe not look as bad. Okay, so what happens with this case is, right, you get, this async keyword is used by your program to indicate that it can run asynchronously. So if you have like a web request or a function that downloads a web request, it has to have the async keyword to let Python know that, okay, this is a program that can be executed out of order, right? So you can basically juggle things around. So if you have 10 programs or let's say one function that is going to run 10 times to download maybe information from 10 different URLs, you can use the async IO keyword to let Python know that, okay, you can run this function 10 times and you can run them out of order. The order doesn't really matter here. So that's one of the key differences. Sub-programs that run asynchronously are generally referred to as a coroutine. So, any program that can run asynchronously or out of order is basically called a coroutine. So this is a sub-component within your program. Sorry, there's a little bit of terminology, so this got a little bit heavy on the terminology, but let me quickly go to the code. So one more thing. So the await, so this is the async keyword, and then the other keyword that you have is the await keyword. So the await keyword basically is used by a coroutine to return control. So I mean, on the previous slide, I told you that, okay, you give control to different parts of your program, but then it's up to those guys to return that control back, right? So this keyword is basically the keyword that is used by those programs to indicate, all right, I'm done. Now you can, take the control back and do whatever you want. Okay, so this is important. So you will see the async and await in the async IO code that you actually see. So let's do our web requests program using async IO. So let's do the same program, but this time with async IO. Okay, so let me quickly introduce this. Don't have a lot of time, so I'm going to quickly go through this. So this is the async IO program. So first thing that you need to introduce is async IO. So you need to import this library. Now notice that you have this download single function that you had in the previous program. Notice that you have this async keyword before this, right? So what that means is once you actually run this thread to download a program from a URL, it can run out of order. So if you have 10 of these that you want to run, these guys can run out of order. But once they run, these guys, it's up to them to return the control. Okay, and then so let's look at the main program first. So we have this URL. So this is just reading the URLs from the text file. Then what I'm doing is I'm kind of, so let me go back. So I'm basically running this download all with the arguments of the list of sites. So I'm basically sending the site list to this download all program or function. Again, download all is also contains the async keyword, right? The async keyword means that, okay, download all is going to download the websites and then it's going to return control back to the main function. So the main function, once you actually run the download all, the main function will have to wait for it. So before it goes to the next line, which is, calculate the download time, it has to stay on hold there and wait for this function to actually complete, right? And what does this download all function do? It basically uses async io.ensure future. So it basically takes all of the download tasks that it has and creates these task objects, right? So you have this task object that you're storing. So you create like 100 task objects, and then you give them to this async io.gather to basically run. So you say, okay, I'm going to kind of create these 100 objects. The objective of each one of these objects is to download data from a specified website using a session that it's going to get. And so once I create these 100 objects, then I kind of indicate the operating. Then I say, okay, here you go. These are 100 objects. Please execute this task, download these 100 websites, and then move on. So that's what you do here. I would like to give more detail, but I'm kind of running out of time, unfortunately. Just you're getting the high level overview, and then maybe you can kind of read this in more detail when you actually get the code, so you can play around with this. So yeah, so this is what is happening. Now let's quickly run this and see how much time gain we get. So remember, with threading, we were getting like 6.7 seconds. Now let's see what happens. All right, about 4.1 seconds, which is faster than the threading part, right? Maybe one more time. All right, this time it was about 3.5 seconds. So now you actually see that this is even faster than the threading library, right? So let me just go back quickly to my slides. Now, why is this faster? Well, this is faster because you're kind of now using the async IO library, right? And that library basically is basically making things faster, okay? So you have this event loop, which kind of takes care of all the threads within Python, and then interfaces with the operating system. So this guy is kind of, or this girl rather, is kind of taking care of all this management. So it seems to be more efficient and probably better at doing the task that you were asking the thing to do using threading. So this seems to be faster. And so if you can use async IO, you should use async IO. It's more preferable than threading. But of course, one of the problems with this is that this is newer, right? So async IO is newer, so it has compatibility issues. So it doesn't work with all libraries, right? So if you go back to the code, you're not really using requests over here. You're using this aio.http, which is to download or process your download requests, right? And why are you doing this? Well, because this requests library is not compatible with async IO. So use async IO, but you may run into these compatibility issues when you're using async IO. Another issue is with async IO, your code seems to be more complex. When you're using threading, the code is less complex, okay? But again, this is something which I feel is a bit more subjective. It is possible that some people feel that async IO is easier to write than threading. It really is up to you. It's more of a personal kind of a thing. And then another thing is this is more cooperative, because a thread will kind of give up control when it wants to, whereas this is preemptive. Now, why is this preemptive? So first of all, what do we mean by preemptive? What we mean by preemptive is that when we send out a thread, the operating system can actually step in and stop that thread if it wants to, Now with threading, this is required because you are sending out your threads into the operating system. And so if things get stuck, you will kind of end up impacting other processes that are running in your operating system. Whereas if you get stuck with async IO, if a thread gets stuck, it's not really going to affect other things because you're getting stuck within Python. So your operating system itself is not going to get affected. So that's a table which kind of, compares async IO and multi-threading. Now, I'm sorry, I had to go a little fast because I had a lot of material to cover. So that was probably my last slide, yes. So that's it until next time. So yeah, if I get time, maybe I'll do another lecture. And if you guys want me to, maybe I'll do another lecture on this topic where we talk about multiprocessing, maybe even threading and these things in a little bit more detail. But I think today we're good with time. So I did it in 1 hour and 6 minutes. So yeah, we're more or less on time. A little bit over time. Now, if people want to ask questions, I am happy to answer questions. Okay. Right. Do we have any questions?
Yeah, we do have, Dr. Hassan.
So just give me 1 second, Dr. Adnan. I think I probably should turn my fan off because I don't have a great speaker. Just give me 1 second.
Sure.
Yes. So let's look at the questions. I think I am getting some questions on the WhatsApp. So
yeah, they're the same from the chat box.
Right.
Okay. So there are some questions here. You can see them.
Sure. Right. So one question was how many maximum threads / maximum workers can we generate per processor? Well, I mean, again, if you're kind of staying within the GIL, you have, you're pretty much using one processor, so you can kind of generate as many threads or maximum workers that you want. But I think obviously, if you generate too much, it will really slow things down because every thread kind of has its own set of, it creates its own overhead, and that of course can kind of cause problems. Okay. You pretty much should not have too many worker threads, I think. Okay, so this is something which kind of requires you to play around with the code a bit. Okay, so another question is when we receive a response from database, would it be in the form of an interrupt or poll? So that was just a simple example that I gave. I mean, I don't know. I mean, it really was just to kind of indicate that yes, with a database, you can kind of get delays. So it doesn't really matter what you're doing. I mean, you could have a more complicated interaction with the database, but right now, what I really wanted to do was to give you guys a more or less a synthetic or a toy example, right? So yeah, you guys probably know about databases more than I do, right? So yeah, my kind of knowledge in that is a little bit limited. Then one more question. Okay, so what if we increase the worker threads? Yeah, I mean, we could. There's no kind of maximum. I guess it could be limited by your system's capability. You could create as many as you want, but what I said was your performance is eventually going to saturate because every thread kind of has its own overhead. So don't create too many. Okay. So executor, a part that's controlling how and when each of the threads in the pool will run. So yes, kind of, yeah. So let me just quickly look at my code. So this is more related to the threading, right? So we have the thread pool executor. So yeah, so you have this executor which kind of gets these 5 workers, and so it kind of manages these 5. So it kind of manages the download requests 5 workers at a time. So this guy is kind of controlling that part. Okay. Okay, so that's another question. Interesting. So we have 100 URLs from data download. We create 5 workers. We have 2,500 web URLs for data download. How should we overcome that? How many workers should we use in that in this scenario now? Okay, that's another interesting question. Yeah, I mean, I don't know. I mean, I think so. There's no magic number here, right? And this is something that I've kind of written on my slides too. There's really no magic number. This is something, especially with threading. I mean, this is something. So, number of worker threads is something that you have to figure out heuristically, or you have to kind of, do this trial and error to kind of figure this thing out yourself. Okay, there's no magic formula, so you have to do some sort of experiments to figure that out. Now with async IO, because async IO kind of manages this thing for you. If you kind of look at this particular program, you can see that I don't really specify any worker threads or the number of worker threads here, right? I'm kind of leaving that decision for async IO to do, right? So maybe you might want to do like 200, 2,500 web URLs. So just plug that into the file, and then maybe use tweak the number of worker threads within this threaded program. And then what you could also do is maybe use this same program for async IO, and over there you don't really have to specify this parameter, and see which one actually works out or actually gives you the better throughput rather, right? So yeah, this would be a good experiment to run actually. Okay. Right, I think that's the end of the questions. Now let me quickly see if we have any questions. I'm going to stop sharing my screen and maybe look at the chat window and see if we have any questions there. Okay, I think that's the end of the question. So, right, so we've had a decent turnout. Thank you, everybody. Dr. Adnan.
Thank you very much. And yeah, it was a very insightful lecture, and I hope everybody got benefit from it. And yeah, we do like to have more session on this, and probably you can focus more on the parts in maybe 2 or 3 lectures, so that it will become more useful for people to learn.
Absolutely. I mean, if people like this session, in fact, everybody who joined, we really appreciate if you guys would actually provide us feedback about how you actually like this webinar, and do you guys want more, and what sort of topics within concurrency and parallel programming would you like us to maybe delve into more detail. But the way that I'm thinking about it is to kind of talk about multiprocessing, and then even threading and async IO and these sort of things in a little bit more detail in future lectures. We could have like a mini crash course, maybe in 2 or 3 more lectures where we talk about these things in more detail. So today things might have gotten a little heavy by just introducing. So I mean, if you don't understand everything on the code, don't worry about it. Kind of a lot of concepts here that are contained within the code. So if you don't understand it line by line, don't really let that scare you. Okay, as long as you get the basic idea.
Yeah, so we will have this recording on our Facebook page, so you guys can watch it later for more understanding, and you can also give your comments, leave your questions there, and I hope that Dr. Hassan will be able to answer them as well. And yeah, thank you everyone again for joining. It's time to say goodbye. Thank you everyone.
Bye.
Bye.